This video will cover the Claisen-Ester condensation. This reaction is similar to the aldol condensation, but it uses esters instead of ketones or aldehydes. Esters can form enolates just like ketones and aldehydes because they also have alpha protons. The ester alpha protons, however, are less acidic than the alpha protons of ketones and aldehydes. The pKa of an ester alpha proton is about 24, as compared to about 20 for a ketone or aldehyde. Esters are less acidic than ketones or aldehydes for the same reason that esters are less electrophilic than ketones or aldehydes. The carbonyl on an ester is less available to stabilize the negative charge on an enolate due to the additional oxygen. We can see why if we consider these resonance contributors to the ester structure. The carbonyl oxygen already has a partial negative charge prior to formation of the enolate. This makes it less available to help stabilize the enolate in the above resonance structures. Now let's consider the Claisen condensation reaction. If an ester is treated with base, it will react to form a beta-keto ester. The product is called a beta-keto ester because it is an ester that contains a ketone at its beta position. Notice that the product of a Claisen condensation is different than the product of an aldol condensation. The product of an aldol is a beta-hydroxyketone, or aldehyde. This difference is due to the fact that an ester has a leaving group. Therefore, the electrophilic carbonyl can reform when that leaving group is kicked off. One more thing to consider for the Claisen condensation is that typically we match the base to the ester R group. In other words, this R and this R will have the same identity. For example, if we use this ester, we will use this base. And if we use this ester, we will use this base. The reason that we typically match the R groups is so that if nucleophilic acyl substitution occurs, we don't see a change in the product. If we use an unmatched pair, such as this, and nucleophilic acyl substitution occurs, we will get a different ester than we started with. This means that there are two potential esters that can react in the Claisen condensation, meaning that we will get a mixture of products. To avoid obtaining a mixture of products, we typically match the base and the R group on the ester. Next, let's look at the mechanism. Let's consider the reaction of this ester. If this ester is treated with base, we will get the following product: a beta-keto ester. The first couple steps of the Claisen condensation mechanism look very much like the first couple steps for the aldol condensation. In the first step, the base deprotonates at the alpha position to the ester carbonyl. This produces the enolate, which is resonance stabilized. The enolate then reacts with another molecule of ester. The nucleophilic enolate attacks the carbonyl carbon of the additional molecule of ester. This produces a tetrahedral intermediate. In this case, the left-hand portion of the tetrahedral intermediate came from the ester that acted as the electrophile, and the right-hand portion came from the ester that acted as the nucleophile, the enolate. In the last step of the mechanism, the carbonyl reforms, kicking off the leaving group and forming the product. The driving force of the Claisen condensation is the formation of the beta-keto ester. The beta-keto ester is much more acidic than the ester starting material. The alpha position can be deprotonated by the strong base present for the Claisen condensation. to produce a very stable intermediate. This intermediate is so stable because of resonance. It is the formation of this resonance-stabilized enolate that drives the Claisen condensation.